Hello and welcome to another video. In this video, we're going to be working on the last problem of Saturday's LeetCode Contest, the hard problem from there. And it's pretty difficult, and it's find building where Alice and Bob can meet. So in here, you're given a zero index array heights of positive integers, where heights I represents the height of the ith building. If a person is in building I, they can move to any other building j, only if I is less than j and heights I is less than heights j. You're also given queries in the format of A and B. On the ith query, Alice is in building A while Bob is in building B. Return array ants where ants I is the index of the leftmost building where Alice and Bob can meet on the ith query. If they can't, then have -1. So if we look at like this example, so for query 0 and 1, Alice is here. We can probably actually make this a bit bigger and just move it down so we can just throw it down here, and then we'll come back and go over the other one. There we go. Okay. So for the first query, Alice is here and Bob is here. So they have to meet at a building to the right of them, and the first available building is this one. So this is index 2, so that's what we get. In the second query, we have 0 and 3, so 0 is here, 3 is here. Same thing, they have to meet in building to the right, which is this one over here, so that's index 5. In the third one, we have 2 and 4. So they have to meet to a building to the right, but it has to be bigger than both, so there is no building there, so we have -1. Then we have 3 and 4, which is these two, so they have to meet over here again. The building has to be bigger than both of them, and to the right. And finally, we have 2 and 2, and they are both at the same building already, so that's just where they meet. Now let's go through this other example, because there are some that we haven't really covered yet. So in this example, let's take a look at it again. So we have query 0 and 7. So I think 7 is the last index, so we have this and this. So in this case, if A is to the left of B, and it'll always be to the left of B, right? We can just sort our query. That's the first thing. For our query 7, 0, we can just always sort it where it's, ascending, because it doesn't really matter. 7, 0, 0, 7 should give you the same result. So if the right person has a bigger building already, then the left person can just simply move to their building, right? So that's the case here, where if the left person is bigger or equal, like let's say they're here, the left person can't move here because the person has to move to a building that's bigger. Okay, so let's go through the next example. So we have 3 and 5, so 3 and 5. So like in this case, this person can't move over here because it has to move to a bigger building. So if it can't move to the one to the right, then they both have to move to the first building that's bigger than both of them, which is right here. So that's index 6. Yeah, and that's what it is. Then in this third query, 2, 5, like I said, we can just flip it around. So we can have 2 here and 5 here. So this is the same kind of case where they can't, the left one can't just move to the right one. And there is nothing bigger than 8, so there's a no solution here. So we return -1. Then we have 3, 0. So like I said, we can just flip it around, make it 0, 3. So 0, 3. First building bigger than both of them is this one. And 1, 6. So 1, 2, 3, 4, 5, 6. So here, the person on the left can just move to the person to the right's building. So let's actually stick with this one for now. Actually, yeah, let's stick with example 2. Let's just move example 1 down, because example 2 pretty much has everything we need, and we can kind of like use this. Okay, so essentially there are 3 types of queries, and 2 of them are really easy. So type 1, they are in the same building. So that's really easy, right? If a query is like 5, 5, they are already in the same building, so we can just return that building. Type 2, the person to the right has a building taller than the person to the left. Right? So like if our query was like, let's say 3, 8 here, or these indices like, 1, 2, we can just say, hey, the person to the left can just move to the person to the right's building and we're done, right? So in this case, we just basically, very easy, return person to the right's building. So notice, by the way, that both of these, we can just return the person to the right's building, right? If they're in the same building, we can return the person to the right's building. And if the person to the right has a taller building, we can return the person to the right's building again. Now the tricky one is, what if the left building is equal to the right building, right, in height? or the left building is bigger, like this. So this is the example we're going to focus on. This is going to be basically all of the code. The other stuff is super straightforward. And I actually, small little disclaimer, I actually did this doing a segment tree, and I'll kind of explain a little bit how that works, but it wasn't the best solution, and it barely passed after I had a bunch of caching. I was like, okay, this beats like 5% of solutions after I optimized it to hell. So this is probably not the way to go. But I will be covering segment trees, just like the general segment tree data structure, in the near future, because I think it's pretty useful and there's almost no content on it. So if you guys are looking for that, it's used a decent amount in the very hard problems. But anyway, let's get back to the problem. So let's just take, we don't need to take this exact, actually we could. Let's take this exact example. Right, so these exact buildings. So we have 5, 3, 8, 2, 6, 1, 4, 6. So let's kind of simplify the problem a little bit, right? Because for these hard problems, it's good to simplify it. So let's just say, given a building, like given this building, let's say, how do we find the first building bigger than that building? There's the obvious brute force, right? We just traverse. So that would be and it's also important to think about constraints for these hard problems. So this is 5 times 10 to the 4th for height length. So if we do like 5 times 10 to the 4th, that's going to be how long it takes to traverse. And then there's also 5 times 10 to the 4th queries. So if it's h times q, that's going to be too slow. So a linear traversal for every building to just manually get its height is too slow, right? But that's like the brute force, just literally go right until you find one. And if you didn't, okay. So how do we improve upon that, right? Just given one building. So you can actually build a monotonic stack for everything to the right of it, right? And basically what would happen, let's kind of walk through how this would work, and then we're essentially going to use this to do the other stuff. So the way a monotonic stack would work is we would simply add numbers, and we can add numbers. Actually, it actually works better to add in this case. We actually want to start at the end, and I'll kind of show you why. So at the end, we want to have a stack of increasing heights, right? Because if our stack to the right is increasing heights and like their indices, let's say, right? Like if we just had like 2, 5, 8, 6, or 2, 5, 8, 10, and our building that we were looking for had height, let's say 3, we can easily just binary search, right? Because we have a linear sorted number of buildings, we can just binary search. See if we find anything. If we do, then that's the building, right? So our goal for a building is to get this kind of format where we want to get a monotonic increasing stack of buildings to the right of that building, right? The way we could build it, easiest way is just use a deck. So use a deck, you start at the end, and basically let's kind of walk through how this would work. So essentially we have a deck, and when the deck is empty, we just put in the number, and then for every number to the left, we just simply check. Remember, we want an increasing stack, right? So if we're putting in a number and that number is bigger than anything in the front, we're going to pop everything in the front, and then we're going to finally add the number. So like when we try to add the 4 is not bigger than 6, so we'll just add it. Then the 1 is not bigger than the 4, so we'll just add it. Now we're trying to add a 6, right? So a 6 is bigger than the 1, so we don't need the 6. We don't need the 1, right? Like why would we ever use a 1 when we have the 6? The 6 is bigger and it comes first. So so the 1 is redundant, so we can get rid of the 1. We can also get rid of the 4, and we can actually get rid of the 6 because we're going to keep track of the number and the index. So a 6 that comes earlier than a 6 later, there's no reason to keep the later one, right? We would just always take the earlier building. So now we just have this 6 right here. So now we add in so I'm only showing the number, but we're actually going to add the number and the index. So we add the 2 is not bigger than anything, and then we are adding the 8, and the 8 is bigger than the 2, so we pop the 2, we pop the 6, and now we have the 8. So for the 3, the monotonic increasing stack of everything to the right just looks like 8. Let's do one more. So let's say we take this. Let's do the monotonic increasing stack. Remember, we're going to start at the right. So we're going to have 6. The 4 is smaller, so we add it in. The 1 is smaller again. Then when we add this 6, we are going to delete all these because this is all redundant now that the 6 is better than all of those. And then that's basically it. So the monotonic increasing stack for this is this. Now the question is, if we have to do this for every single building, that's also not great, right? Like to build this stack for, let's say, this index, the problem is we have to traverse all the way to it, right? So we still kind of have an n-squared solution. So how do we solve our issue of, you know, we don't really know, or not we don't really know. How do we solve our issue of, can we build it somehow and maybe use it for future problems? And it turns out we can. So what we can do is we can take our queries. So let's actually take our queries. So let's write them down. And I'm kind of going to walk through the exact process here. So let's say we have 073552. So let's write those down. So we have 0735. 3552 and 3016. And we are basically going to group our queries into 3, and we're also going to add, so for our queries, we're going to, every query that we can answer quickly, we'll just answer quickly. So I'm not going to show this writing into the result, but essentially we'll keep an index for the queries. So we're just going to go through our queries, and we're going to take every single query that we can answer quickly, and then we're going to keep only these hard ones left, right? So this 1 and 2 is very easy. We can do it right away. And this 3, where the left is bigger or equal to the right, is the one we're going to be adding into our hard queries that we need to do the stack for. So let's kind of walk through this. So for 0, 7, 0 is over here and 7 is over here. We can even index these to make it a little bit easier. So 3, 4, 5, 6, 7. So 0, 7 is very easy, right? The right is bigger than the left, so we can immediately just get an answer. Like, we know they have to be here, right? So this is just going to give us a 7, which is fine. So we don't need this one in our final answer. Like, this is just done right away. Let's look at 3, 5. So 3, 5 is one that we can't solve right away because 2 is bigger than 1. So we can't just move to the right one. 5, 2 we will reverse. So we will reverse it into 2, 5. 3, 0 we will also reverse. So 2, 5, let's take a look. So 2, 5 is 2 and 1. So this is going to be a hard one again. We can't just insta get an answer. 0, 3, hard one again. And 1, 6. So this one we can get an answer right away. It's just going to be, they just move to this index over here. Right, so this one should be 6. So this one we basically did. And we also did this 0, 7, right? So we should have 3 queries left. Oh, let's take a look, actually. Maybe I have too many queries. That's possible too. So I have 5. I think oh yeah, right. I can get rid of this one as well. Right. So this one is done because it's basically right away. So now we have it correct, where we basically did this one and the first one. We have 3 queries left. So what we're going to do now is we're going to sort these queries, and we're going to sort them by end time, and we're going to do it in reverse order, and I'll kind of show why that is. So we're going to sort them by end time. So 5, 3, this one will be first, right? 3, 5. Then 2, 5. Then 0, 3. These are our 3 queries that we left. And the reason we want to sort them by end time, so let's just also get rid of all of this. These are the hard queries that we have left. And let's also get rid of these arrows, because we're going to be building our stack, and we want to index these buildings by the right building going left. So that way we can be building our stack, and then when we keep going left, we'll just add on to the stack that we had. So let's kind of walk through how this would work. So for this 3, 5, these are our 2 locations, right? 3, 5. So basically what we need is we need to build our stack. So first let's build the stack, right? So we're going to build a stack. So I already showed this before, but our stack is we're going to first add the 6, and we're going to build our stack up until an index that's greater than this B index, right? So we're going to build our stack. We're going to have a 6. We're also going to have a 4. So this is our stack. This is our monotonic stack. It's actually a queue, I guess, but either way, right? Increasing. And like I said, it will have the number and its index, so we can easily find it. So now basically all we have to do is we have the 2 and the 1, like we have these 2 numbers. Now all we need to look for in the stack is the smallest index. So we can write this down. Smallest index that is greater than A, right? And remember, if this is A and B, right? So this left one is A, so we can write that down as well. So, or then the left building. Because if the right building was bigger, this would be one of our easy solutions, right? And if they were the same, then it also works, right? If they're the same, you can use A. If the right one's bigger, you can use A. So essentially, we're looking for a building they can both travel to that's bigger than A. And so we can just easily binary search in here and find that, the smallest index is this one over here, right? That this value is greater than A. So that query is solved, right? That index is going to be 6. So that's going to be, so this one was solved already. Now this one is solved. Now let's keep going. So we solved this query. Now let's keep adding to the stack to get to the next query. So next query is 2, 5. So for 2, 5, our stack, the last location we filled was right over here, and our right building is still in the same place. So we don't need to add anything else to the stack. So once again, we're doing the same thing, except now our left building is 2. So we're looking for the first building that's bigger than 2. Well, that's this one again. So that's going to be index 6. So for this 2, 5 query, this index should be 6. Let's take a look. Oh, did I screw that up? 5, 2. Maybe I did. Oh, right, I did, yeah. So I screwed up because 2 is actually over here. So instead, we're looking for the first building bigger than 8, right? So for the 3, it was 2, but for the 2, the leftmost building is 2 now. So for this is 2 instead of 3, and 2 is 8. So we're looking for the first building bigger than 8. It doesn't exist. So we return -1. So now that's correct. Okay, now we have one more query. So we're done with this one, and we're done with this one. Now we have one more query, and now our rightmost building, we need to update it, is now 3, which is over here. So we need to keep building our stack. So like I said, we're going to keep track of the index where we are. So we were on this index when we were building. So now we need to keep building it until we get the rest of it, right? So we try to put in a 1, we can. Now we try to put in a 6. And like I said, the 6 will get rid of all of these values because these are redundant because the 6 is bigger or equal to them all. So now our stack is basically just a 6. And our leftmost building is 0. So now for our 2 buildings, we look again. We're looking for a building bigger than 5 and in our stack, and that is 6. So the 6 with an index of 4. And so that is what the answer is. So basically, to sum up, what we need to do is first we solve the easy queries, then we put the hard queries into some kind of data structure like a array or something. You sort the array by the b value decreasing because essentially you want to be traversing this way. So then as you're traversing, you can be building your stack. And then you can reuse that stack for everything else. So now the total cost of building our stack is n, right? Or I guess this would be like heights or something. We also had to sort our queries. So that's going to be like q log q. And we also, for each query, have to do a binary search, right? So that's going to be like h log h. That's going to be like heights plus q log q plus h log h. These are 10 to the 5th each. So this is going to pass. So now we can code it up. Like I said, there's kind of a lot here, right? We had to use a deck. We had to use a monotonic stack. We have to sort our queries and keep indices. That's another very useful thing. If you want to sort something but know its original index, you just add an index property to that item and you add it in the end because it gets sorted by the first couple things. So we have to do a lot of things here. And that's kind of like these hard problems are. It's basically like 2 or 3 medium problems in one. Okay, so first we're just going to declare our result and we'll just initialize it all to -1. So result -1 times length queries, right? Then we're going to have the rest array, and this is going to be the hard queries. So you can call this hard if you want. So now we have to go through all of our queries. So we'll say for I query and enumerate queries. Remember, a query can be reversed. So we're just going to sort it really quick because that costs nothing, right? If our query is like 5.2, we want to have it in 2.5. You can also just use the max, but I'll just do it this way. A b equals sorted query. So that way A is guaranteed to be the leftmost value. So now remember, we have our 2 easy cases, right? So if A equals B or heights B is greater than heights A, right? In any one of those, then our answer is basically just go to building B. If they're the same building, it's building B, and if building B is bigger, go to building B. So we can say result at index I for the query equals B. Otherwise, we're going to append this query to the hard query. So we'll say rest dot append, and we're going to append a tuple of, so the way we're going to append, you can do this a few different ways. We're going to append like this, IAB, It doesn't really matter because like the order of your A's doesn't matter as long as your B's are in reverse sorted order. Like it doesn't matter at all. As long like so you can have so if you process like 2-5 before 3-5, like it doesn't really matter. Okay. So essentially our query is going to be index IAB. Now we need to sort our queries by the B index. So we'll say rest.sort. And if you want to sort by the second index of the tuple, what you can do is you can make a lambda function. So you can say key equals lambda takes in an x and just returns the second element in x. And we want it in reverse, so you can say reverse equals true if you want to reverse sort. So that's how you do, like, you can sort by any element. If you wanted this element here, you would do x1, you know, and whatever you want. Like, it's basically a custom sort function. Really easy, really good. Okay, so then we're going to have this, like, monotonic increasing stack. It's not going to be a stack, it's going to be cube. So we'll call this mono equals dec. And the index, we're going to keep track of the index of, like, how far we need to keep going to build our stack, right? We want to build our stack up until the index right before the rightmost building, right? We don't want our stack to go into the rightmost building. We want it to build every building to the right of it. So we'll say we'll initialize some index, and that's going to be the very last index in heights, right? So we'll say this. So we need to destructure this. So we'll say like for I, A, B, because this is the format in rest. We basically need to keep building our stack until the index is the building that we care about, right? So let's say, you know, we had some numbers like this, and our stack was on number 5, and our rightmost building was 2. We need to keep building our stack until the index of the stack is the same index that we're on. Then we stop. So we'll say while index is greater than B. And so now we need to remember our stack needs to be monotonically increasing. So as we're going to be popping and popping left, but before, or appending, or sorry, we're going to be appending left and popping left. But before appending, like I said, if we have a number that's bigger than all these, like a 6, we need to keep popping from the left, and because these are all redundant, right? If you have a bigger building that's before anything else, that's always going to be the best solution. So we'll say while the stack exists and heights index is greater than or equal to, right? If you have a 6 and another 6, you still want the one that comes first. So heights. So it's basically a monotonic increasing stack, but you're building it backwards. Normally you're building from the right. Now we're building it for the left using a cube. So we'll say mono.popleft. And then once that's done, we will append index. And no matter what we did, either way, once we put that thing on, we will decrement the index, and we'll keep doing this until the index is equal to the building we're on, and then we won't put that building on. And then when we go to the next building, we'll keep adding more and more and more. So we are growing our stack as we are traversing left. Okay, so I'm just going to initialize a location to where they're going to travel to -1, and then if I don't find anything, that's what I will be adding to the result. So now we basically do like a normal binary search. That's another thing I guess we do in this problem. So we literally do monotonic stack, binary search, sort with an index. There's like 4 things. So it's kind of low. So you can also use bisect if you want to, like for these harder problems. Once you've done enough binary searches, you can use bisect. I personally haven't used it very much, but Python does have like a bisect right and bisect left, so you can write your binary search in one line code if you want to. Because I think for these level of problems, you're not super concerned with like, can I write a binary search anymore, right? It's expected that you are able to do it. So essentially, what we need to do is we need to actually loop from where our stack is, or not from where our stack is, sorry. We need to loop from 0 to the length of our stack, right? So basically our monotonic increasing stack, we're going to loop from 0 to the very last index. So we're going to check every single number in there. And remember our monotonic stack, it doesn't actually have a value, it has an index. So in going back to this picture, when we are creating our stack, we're not actually adding the values, we're adding the index. And then we can just check the index and height. So instead of adding like 1, it will add the index, which is totally fine, right? So it just makes it easier to work with. And then we are actually checking this like heights. So we are going to loop through our entire stack and look for the leftmost element that is greater than B. So that should be pretty straightforward to do. So we'll say while left is less than or equal to right. We get a pivot point. And then we just say like if heights. So like I said, the stack has an index, not a value. So if heights mono P is greater than heights A, remember because A has to be greater than or equal to B because these are the hard queries. So if this is the case, then this index is the best so far. So we take this index and then we see if there's anything to the left of that. So we'll say location equals mono p, right? Whatever index is stored in the actual monotonic increasing stack. And then we need to go left to see if there's anything better, right? So we found a building, and then we're going to see if there's anything left of that building that also satisfies this. Otherwise, if this building is too small, then we have to go right. So let's just go right. And finally, we need to actually append. So remember, this I is the original location in the queries. That's why we added this index into it and sorted it. So if you want to have queries and you want to sort them, but you want to know the original location, just add an index. So result I equals location. And if we never found anything, it will just do -1, right? If we never found this, this will never change, and we'll just return -1. And finally, we just need to return the result. So quite a long one. Let's see what happens. Okay, we have some errors. So let's see here. Let's go over here. Rest is not defined. So this should actually be, this one should be rest, right? This is the rest of our queries. Maybe not the best naming, but yeah. Okay, there we go. Oh yeah, so you can see it's pretty efficient. To go through, I guess we could go through the time and space. It's going to be a lot. So let's go through this individually, right? So start off, we are going through our queries. So to go through our queries, that's going to be O of Q already. So let's just add that in. So we'll use Q and H. We have to sort our queries. Worst case scenario, every query is in here. So that's already Q log Q. Then we have our monotonic increasing stack that we're going to be building. So that's obviously going to be worst case of H. And for every single building, we have to do, for every single building in queries, right, we have to do a binary search. So that's going to be like, this is going to be H here to actually build the monotonic stack, because worst case scenario, we have to like actually go and build it all the way down. So that's going to be O of H. Let me see if there's anything else here. Yeah, right. So this for this binary search, so we're basically searching through the stack, which is length H. So it's going to be a log of H. And then how many times are we doing that? Well, we're going to be doing it for number of queries, right? So for every single query, if every single query has a tough query, then it's going to be like Q log H or something like that. That's going to be something like this, but because Q and H are 10 to the 5th, and log n for both is totally fine. Like adding them together is totally fine, right? So this is fine. So it's going to be like something like this. Maybe I missed a little bit, but something like this for the time. For these, there's like so many things that it's kind of hard to like have it all. Okay, so let's look at the space. So we have our result, which we don't count. We count the rest of our queries. So that's length of Q, right? Every query that is a tough query, we're throwing it in here. See if we have anything else. We also have this monotonic increasing stack, which can be worst case O of H. So that's Q plus H. And I think that is it, right? So we have the monotonic increasing stack, and we also have our queries, which is O of Q. And yeah, I think that should cover it. So yeah, the other thing, like I said, you can do this doing a segment tree, and I will briefly go over how basically what you could do is instead of doing this monotonic increasing stack, you can have a building, and you can actually calculate using binary search to find a maximum. So basically what you would do is, like let's say you're at this building 2, you would split the rest of the buildings. Starting in the beginning, you would get a pivot point. Let's say it's like somewhere, or let's actually draw it down here really quick. So let's say we have a building here. We have some numbers like this, and we are looking for a number that's bigger. Let's say the number is actually like on the left side. Like this. So basically what you would do is like if it's this number and these numbers after, you would get a pivot point, and then you would check, you would split this into 2 parts. So let's say this part and this part. You would say, okay, can I get the maximum here? And if the maximum here is bigger than 5, let's say is the number I need, then I'm gonna search deeper in here. And if it's not in here, then I'll check the maximum here. And if the maximum here is greater than 5, then I'll search deeper in here, right? So you can get rid of half at a time. And basically the way to get a maximum in a range in log time, so it's going to be like log n times log n time complexity, is you would use a segment tree with all your numbers, and I will be making a video discussing segment trees on maximums and sums and stuff in the future. But yeah, so that's going to be all for this one. So hopefully you liked it. Definitely, if you do want a super hard problem, doing this with a segment tree I think is significantly harder than the monotonic stack. So if you want to try that, and also actually having it pass on LeetCode is also very difficult. So if you do want a super hard problem, doing that could be fun for you. Okay, but yeah, that's going to cover everything I wanted to cover. So hopefully you liked it. If you did, please like and subscribe, and I'll see you in the next one. Thanks for watching.